Here's a video lesson on Objective 6 from Practice Test B, gas laws and the stoichiometry. Gas laws really is the PUV equal inert equation and then a mole mass problem. So let's take a peek at our first one, Objective 6. It says we're going to react aluminum metal with oxygen gas to form solid aluminum oxide. Well, let's first of all get our equation written. We can't do any stoichiometry unless we have a balanced equation. So practice test B, objective number 6, question 1. Aluminum metal is Al. It is in the solid state of matter. And no, you're not required, but it sure doesn't hurt to keep practicing those states of matter adjectives. It's reacting with oxygen gas. We know oxygen is in molecular form, O2. This pattern of change is called a combination. When a metal combines with a nonmetal, it will do so based on charge. Aluminum, when it hooks into a compound, carries a +3 charge. Oxide, when it's hooking into a compound, will carry a -2 charge. And we simply crisscross and we come up with Al2O3, aluminum oxide. Of course, we then need to balance, finding our stoichiometric ratio. I notice I have an odd number of oxygen on the right with an even, so I'm going to repair the oxygens first, combining those two 6s, 3 O2s, and 2 units of aluminum oxide, give me 6 oxygens altogether, and then of course repairing the aluminum, so we have a 4:3:2 stoichiometric ratio. Now we're ready to consider what the question's asking. If an enclosure with a volume of 4.382 liters has a partial pressure of oxygen of 5.5 times 10 to the -3 torr units, same as a millimeter of mercury, and the temperature is 47 degrees Celsius, what's the mass of aluminum that will react? Well, let's consider what those numbers are giving to us. Now I'm going to just create a little tally by the information. Ready? We have a volume of the gas. Now, it makes no sense to talk about a gas for aluminum. It's in the solid state. It makes no sense to talk about a gas in the aluminum oxide. It's in a solid state. The only gas that could occupy a volume here is the oxygen. So underneath it, I'm going to give that information. It tells us this oxygen is occupying 4.382 liters. It's exhibiting a pressure of 5.5 times 10 to the -3 torr units. Torr is the same as saying millimeters of mercury, mmHg, and it's 47 degrees Celsius. Here we have a V, we have a P, we have a T. What mass of aluminum will react? So this is what we want to know. This is our given quantity. All right, all the information given for oxygen, we want to calculate the mass of aluminum. Well, understand, given a P, a V, and a T, we can PUV inert first, followed by the stoichiometry twist, moving that back to aluminum. I like to get my PUV inert parentheses ready so I can just plop them into the correct parenthesis. PV equals nRT, and when I do so, I can just simply place them and we'll decide on the algebra. So the pressure given here is 5.5 times 10 to the -3, write your unit, torr units. As soon as I write P, I also know the R constant. Make sure you're matching the R constant. 62.4 is the millimeter mercury, also called the torr, ideal gas constant. Volume given already in a liter, so that's perfect. Must be in a liter, and it is. And we'll need a Kelvin temperature. 10, carry my 1, about 320 Kelvin units. We're going to solve for N, the number of moles, and that mole number is oxygen. Alrighty, so let's hit. We want to do the side without the variable first, so we're going to hit P times V divided by R times T. So calculators, everyone hit with me. Make sure we're getting a common answer. 5.5 E -3 times 4.382 divided by parenthesis 62.4 times 320. Close your parenthesis, and we have a number for the moles. 1.2, I'll say 1 times 10 to the negative 6, pretty tiny number. So now we have a mole number for the oxygen, 1.21 times 10 to the negative 6 moles. Here we see that beautiful tie-in, moving from moles to mass for our stoichiometry. So we define that heart of the problem. So in the second part of our problem, we're going to begin with that same number we just calculated. That represents the moles of O2. Taking me right into the heart of our stoichiometry problem, where we want over given. Keep in mind our target, grams of aluminum. We want to know aluminum. Its coefficient is a 4. Starting from the oxygen, its coefficient is a 3. 3 moles of O2. So the ratio, 4/3. To find a gram unit, we need the molar mass of aluminum. So do you have a number, unit, label, every step, every time? And let's hit to see. So the moles, still on my calculator screen, times 4 divided by 3, times 27, the molar mass of oxygen. And I'm finding 4.35 times 10 to the negative 5th grams of aluminum. Take a moment, process this, make sure your calculator is matching mine, and when ready, start the video again. We'll go on to the second question. That next question, right along with the same recipe. In the same reaction, how many grams of aluminum oxide form, assuming we only have a 90% yield? So 90% is the efficiency of our reaction. So we have a new target. Let me go back to this recipe up here. Looking at the target here is how many grams of aluminum oxide, how many grams of product forward, keeping in mind we have a 90% efficiency. We're going to make 90% of our theoretical yield. And I still think the best way is to start with this value as our given. We just have a new want. We want to know aluminum oxide. So for the letter C, start with the same Puvnert value we had for the moles of oxygen. We set up a ratio where we, heart of our problem, want over given. We want aluminum oxide, and I'm only going to take 90% of it. There's the percent efficiency. So by the time I'm done calculating, I'll just get it ready here, I want 90% of my answer. So here we'll have 90% of our theoretical value. There, I got it. So what do we want? We want to know aluminum oxide. Its coefficient is a 2 from the oxygen. So the heart of our problem, the ratio, 2/3. We see that there are 2 moles of our product, aluminum oxide. For every 3 moles of oxygen consumed, 2/3 is our ratio. I'll need a molar mass of Al2O3. So I'm doing a little margin work here. Aluminum is 27, and there's 2 of those in the formula. Oxygen is 16, and there's 3 of them in the formula. So I'm finding a molar mass here of 102 grams of aluminum oxide in every mole. Alrighty. And now what was this 90% for? Just kind of a review. 90% is the efficiency of our reaction. So it's taking our theoretical yield and turning it into an experimental yield. So the percent yield put in there as a decimal place. So I want only 90% of that calculated answer as my final. So let's hit together. I have 1.21 E negative 6 times 2/3. Whoops, I hit a key error. There, I got it fixed. 1.21 E negative 6 times 2/3 times 102. And if I hit equal there, I'd have my theoretical or calculated answer, but I want my experimental. So I go times 0.9, and my experimental yield, 7.41 times 10 to the negative 5th grams of aluminum oxide. Pause the video, process this in your mind. Go through the steps. Keep talking to yourself about the steps. And when you feel ready, let's read the next question together. We're going to combust in our second equation. The complete combustion of liquid hexane. Each product is in the gaseous form. So hexane, C6H14. Our stoichiometry is only as good as our balanced equation is correct. So let's get this written. Hexane, C6H14 in the liquid form, is combusting. We add oxygen, and I know it's going to be quite hot. Out comes some carbon dioxide in the gaseous form and some water in the gaseous form. Alrighty. Let's work to balance. I always like to do C's, then H's, then O's. See where that lands us. So I start with my carbons, repair those first by placing a 6. I count 14 hydrogens, so I repair that by placing a 7. Then I count my oxygens. We have 6 times 2 is 12, 7 on the water. We get a total of 19. So ran into a problem. I'm not allowed to leave a fraction. 19 halves would actually balance that, but that's against the rule. So we erase, start over. No worries. Trick there. Since a 1 didn't work here, let's just double that fuel. Let's double the amount of C6H14. Still working, C's and H's and O's. There are 12 carbons now on the left. 14 times 2 is 28, so I'll need a 14 in front of the water. And now let's see. 12 times 2, we have 24 oxygens here, and 14 more. Total now is 38, so that coefficient of 19 balances this equation. So the old double the odd number trick when that happens. 2, 19, 12 to 14 is our stoichiometric ratio. Now let's read what the problem asks us to solve for. What volume of oxygen gas, measured at 50 degrees Celsius, 1.98 atmospheres, is needed to react with 30 grams of hexane? So let's go back and tabulate what we're given and what we want to know. So tabulating. What is the volume of oxygen gas? So what is the volume? There's my target variable. It's being measured at 50 Celsius, and the pressure is 1.98 atmospheres. And we're going to react 30 grams of our fuel called hexane. Alrighty. So keeping in mind, this is our given, and here is the target. This is what we want to solve for. When I look at this, I don't have enough to Puvner at first. I have too many variables. I don't have an N, I don't have a V. Therefore, because my target is in the Puvner problem itself, I know I have to do stoichiometry first. And what I want to calculate for is an N, the number of moles of oxygen. So I have enough variables to pull out the volume. So we're going to start with stoichiometry, little mass mole problem. 30 grams of our fuel, C6H14, where I do a step 1, step 2, and stop. I only want to go as far as moles of oxygen because that's the N in the Puvner problem where I can then pull out the volume. Alrighty. So step 1, step 2, we divide, we ratio. We need a molar mass for our reactant, C6H14. I know carbon is 12 and there's 6 of them. Hydrogen 1 and there's 14, so let's tally that. 12 times 6, add on 14. I got a molar mass of 86 grams. Ready? We want to know oxygen. Its coefficient is 19. Given the fuel, hexane, its coefficient is a 2. So we divide, we ratio, we stop. Given the amount of fuel, we want to know the moles of O2. So hit with me. Did you hit 30 divided by 86 times 19 halves. The number of moles for oxygen, 3.31. We'll round there. 3.31 moles of O2. Now I'm seeing enough variables to PUV-NERT, pulling out the volume. So PUV-NERT problem is our second step. I like to get my PUV-NERT parentheses ready so I can just plunk in the correct values. I know PUV equals NERT, and the target variable here is the volume that the oxygen is occupying. So I'll just know that volume is my target variable. Here's what the information said. The number of moles we just calculated, 3.31. There's the N value in PUV-NERT. Volume is target, 50 degrees Celsius, 323 Kelvin units, 323 Kelvin. Pressure, 1.98 atmospheres, so therefore I also know the R, 0821. August 21st is a date that I remember the R constant from, so that's my little trick to remember R, 0821, August 21st, the PUV-NERT constant. What is V? V, I know, will come out in a liter, as they always do. So always calculate the side without the variable first. So NERT, nRT, divided by P. So 3.31 still on my calculator screen. I'm sure it's on yours as well. Times the constant, 0821, times the Kelvin temperature, 323, divide by your pressure, 1.98. You get 44.38, I want to say 44.4, somewhere in there, however you round. I'll carry 2 decimals. 44.38 liters big is the size that the volume is occupying. What volume of each product is produced under the same conditions? So we have 2 more products here to calculate for. We calculated for the volume of oxygen. We're also calculating for the volume of carbon dioxide, and we got to calculate for the volume of water. Well, interestingly, we have the mass given, and we went over to calculate volume of oxygen. We had to do a stoichiometry problem to get moles of oxygen. Notice that every one of these coefficients is different, and that's by design from when we balanced our equation. So we'll have to find the new mole ratio and then put it into a PUV-NERT problem. Alrighty, so a little more work involved for this next part. I think what I'll do is we'll put on letter C. I know I have 2 problems in here. So let's just target the first, since it's written first, I'll target the first product. Given 30 grams of carbon dioxide, 30 grams of the fuel, and that's hexane, we want to know carbon dioxide. Alrighty. So here's the stoichiometry first. We have 30 grams of C6H12. I want to know how many moles of carbon dioxide. Alrighty. Now that first molar mass was determined already. It was 86 grams. So I'm just going to put that in here. 1 mole is 86 grams. And heck, while I'm setting up problems, why don't I get this guy ready as well? I know that I have a second target. I also need to know moles of water. Sorry. And I'm just getting both ready because I can set up my stoichiometric ratios pretty easily once I have those parentheses set up. I keep hitting the page, sorry. So 86 grams is the molar mass of C6H12. Alrighty. Now how about the ratio? Want over given if carbon dioxide, its coefficient is 12. So we have 12 halves for carbon dioxide. And then I can just kind of see we'll have 14 halves when the target is water. So 12 and then 14. Coefficient in front of carbon dioxide is 12. Coefficient in front of the water is a 14. So I'm just kind of sliding my work back and forth. And this one I know was a 2. And we're just getting the work set up so we can hit out for N, the number of moles. Alrighty. So two separate little problems here, starting with the same amount of fuel. We're going to target for moles of carbon dioxide, and then we'll target for moles of water. So 30, I'll start that journey there on the stoichiometry map. I'm going to divide 30 by 86, multiply it by 12 halves. For this mole value, I'm finding 0.6976, 0.697. Should we just round to 0.70? That might be good enough. Let's start that second problem. 30 divided by 86 again, times 14 halves. I get 2.44. Oh, I better hit that again. 30 divided by 86 times 12 over 2. This is my error. I knew those numbers had to be more close, so I knew I had a calculator mistake. So, sorry about that. Let's double check my math. I knew something was wrong. I'm going to start with this first problem. 30 divided by 86 times 12 halves, which is 6. Yeah, this is 2.09. Sorry for that, but I made that correction. And then the second problem, 30 divided by 86 times 14 halves, which is 7. This is 2.44. There I go. Alrighty. So now what? I have the number of moles of each. Ultimately, I like to get my PUV-NERT parentheses ready. And I know I'm going to involve two different parentheses here because I have two targets. Alrighty. But a lot of these variables will indeed be the same. Alrighty. So I know PUV equals NERT. Alrighty. Here's the number of moles of carbon dioxide, and then my second problem will do for water. So here we had 2.09 moles, and here we had 2.44 moles. We're solving for the volume. Volume will come out in liters. Alrighty. And from up here, these are the same conditions, 1.98 atmospheres. And therefore we know the R constant, 0.0821. And what was that Kelvin temperature? 323. So this volume, once we solve for it, will give us volume of carbon dioxide. And this volume, once we solve for it, will give us the volume of the gaseous water. So let's hit. We've got to solve for volume of carbon dioxide, and we've got to solve for volume of water. So two more answers here, and these will come out in liters, as all PUV-NERT problems do. So starting on the side, I'll do CO2 first, just because it's written first. I have 2.09, start on the side without the variable, times 0.0821 times 323, divided by 1.98 atmospheres. 27.99, we'll just leave it, 27.99 liters CO2. Certainly you could round that to 28. And second scenario, 2.44 moles of the water times our constant 0.0821 times the constant, the Kelvin temp, 323, and divide out the pressure, 1.98. How about 32.6, I'll round that 68 liters. And you did it. A++. Come test day, we'll have a problem very similar. Keep in mind, one of the problems here, we did the way up high when we first started the journey with aluminum metal, how we did a stoichiometry problem to find the mass. We PUV-NERT first, then the stoichiometry. And down here in the second problem, we did the stoichiometry first, followed by the PUV-NERT. All right, you can probably expect the same strategy come test day. When you have indeed finished this video and given yourself an A++ for perfection, you're ready to go to the next video, taking a look at distributive practice.